Hello everyone, I hope you're all having a great time at the conference. And first of all, I would like to thank the organizers for making this conference possible. And I am really sorry for not being able to attend this conference in person because this unusual situation. And I hope to meet you all at the future conferences. My name is Hayder Hashim. I am from University of Debrecen. And today I would like to talk about the result that I have got with Tanguy Alminar from University of Debrecen, which is about cryptanalysis of ITRU crypto system, which I will call it as ITRU crypto system. So before I go deeper to talk about the technique that we use to break this crypto system, I would like to give a brief history or introduction about the ITRU crypto system. Then I will go back to the technique that we used to break this crypto system. The ITRU crypto system, in fact, is a public key crypto system proposed in 2017 by ITRU, Salah, and Mohammed, and actually it is considered as one of the well-known variants of ITRU crypto system, or the nth degree truncated polynomial ring crypto system, which is a really well-known public key crypto system. And actually, I will call this ITRU crypto system as ITRU crypto system. And since the ITRU crypto system is a variant of the ITRU crypto system, I will go to talk briefly about the ITRU crypto system and the idea of this crypto system, and then what the authors modified on this crypto system to obtain the ITRU crypto system. Then I will go back to talk in details about the ITRU crypto system. The ITRU crypto system is a public key crypto system proposed in 1996 by Houston paper and Silverman, and actually it is considered as really fast public key crypto system, and it has really nice features. For instance, this crypto system is considered as a lattice-based public key crypto system, and also it is considered as the first public key crypto system based on the ring, polynomial ring of this form. And comparing this public key crypto system to other public key crypto systems, this crypto system will have really nice features. For instance, it is reasonably short, easily created keys, high speed, and also it has low memory requirements. Moreover, the encryption and decryption procedure of this technique depends on a mixing system represented by polynomial algebra combined with clustering principle based on elementary probability theory. And finally, what I wanted to talk about the ITRU crypto system is the security of this crypto system. From the lattice-based structure of the ITRU crypto system, this crypto system has very nice security, which depends on the hardness of solving the closest vector problem, which is, or it's called the CVP, which is a really well-known problem. So this is all what I wanted to talk about the ITRU crypto system, and if anyone interested to know more about the ITRU crypto system, I refer them to check the paper of ITRU crypto system, which I will mention at the end of the talk. Now let's go to talk about the ITRU crypto system and see first what the authors modified on the ITRU crypto system to obtain this crypto system. In fact, the structure of the ITRU crypto system exactly similar to the structure of the ITRU crypto system, except the authors here propose to use the ring of integers instead of the polynomial ring. And this actually will lead to really easy way to create the parameters. So let's go to the parameter creation and see how can we create these parameters. First of all, we have an integer b, and we call it small modulo. And also we have random integers f, g, r, such that f is invertible modulo p. And also here we have a prime number q, and here we call it the large modulo, and such that q greater than p times r times g plus f dot m, where, or times m, where m is the representation of the message in the decimal form. In fact, here the authors of the ITRU crypto system propose to work on the message like encryption, which means here the characters we are dealing with are English characters from A to the Z in the capital and small letters. And according to this table, a SCII conversion table, we have A presented, for instance, by 97. And here also the private and public keys can be created easily. The private key is presented by F sub P congruent to F inverse modulo P, and F sub Q congruent to inverse modulo Q, and this can be computed easily using the extended Euclidean algorithm. And also the public key is presented by H and Q such that H congruent to P times F sub Q times G modulo Q. And here the encryption formula can be done by this encryption formula, which is E congruent to R times H times plus M modulo Q. And when the receiver gets the ciphertext, the receiver has to recover the plain text using the private keys, and this also can be done by first computing A such that A congruent to F times P modulo Q, and then multiplying this data result by F sub P modulo P, and this will recover the plain text back. This is actually the idea of the parameter creations of the ITRU crypto system. And in fact, the authors here of the ITRU crypto system proposed or claimed some comparisons between the ITRU crypto system and the classical ITRU crypto system. And here they are. For instance, they claim that the ITRU crypto system has a simple parameter selection algorithm comparing to the one of ITRU crypto system, and the other one, the ITRU crypto system, has a successful message decryption. However, in the ITRU crypto system, there is decryption failure. And finally here, the ITRU crypto system has a better security than the ITRU crypto system, because the security of the ITRU crypto system depends on the hardness of solving the integer factorization problem, which is really well-known problem. And as you all know, this problem is used in many public key crypto systems. So this is what actually I wanted to talk about, the idea of the history of the ITRU crypto system and its modification on the classical ITRU crypto system. So now allow me to go to talk on the technique that we use to break this crypto system, which is the ITRU crypto system. In fact, from the construction of the ITRU crypto system, we see this ITRU crypto system is presenting us a substitution cipher. And as you all know, one of the well-known attacks against substitution ciphers is presented by the frequency analysis technique, which is a technique focusing on studying the number or the frequencies of the letters and the number of their appearances in the ciphertext. So we employ this frequency analysis technique with the help of the SageMath software to recover the plain text without having the private keys. And as you all know, most of the well-known attacks against public key crypto systems focusing on recovering the private keys in order to recover the plain text. But in this crypto system, we used simple frequency analysis technique, and here actually we recover the plain text using only or having only the public key and the ciphertext message, which encrypted using the ITRU crypto system. So now let's perform the idea of this attack in the following steps. The first step is the implementation of SageMath for the ITRU crypto system. Since I just said the idea of this attack is performed using the SageMath software. So first of all, I will go through the implementation, and then we talk about the attack technique, and we perform this attack on like a message. So in fact, first of all, since we have Q, as I just mentioned in the structure earlier, we have Q is greater than P times R times G plus M. Therefore, here we have to have a bound for the representation of the characters. And since we have our characters are presented by English characters from A to the Z in the capital and small letters. So here actually, according to the ASCII table, we have the maximum value for these characters presented by 122. And in fact, here in our implementation in the SageMath, we made this like this bound can be arbitrary. So you may use any maximum value for this your representations as you like. So here let's see like this implementation, like how and perform this implementation on the following example. In fact, in the following example, we used the upper bound is 255. And let's see the input of this implementation. So here, for instance, we have this arbitrary message, which is a cryptanalysis, and you may use any message you like. And here we have R is 8, and we have P is 1000, and here we have this random integers, F and G, and M is the representation of the characters presented by ASCII code, and here we have Q, which is the large modulo. In fact, here, as I said, we use the maximum values for the representations presented by 255. And here we have the private key, and here we have the public key, and here we ask it to print the input. Then here we have the encryption formula, and here when the receiver gets the ciphertext, the receiver has first to obtain A by multiplying these blocks of the ciphertext by F, then multiplying the later result by F sub B, and here we can recover the plain text easily. Let's see like the output. As you see here, this is the output of our previous code, and here we have our message, and this is the representations according to the ASCII code for this message. And here we have Q, and here we have our public key H, and here we have our private key, and here we have the representations of the corrupted message, and here we have the representations of the, in fact here, the representation of the decrypted message. And as you see here, the representation of the decrypted message exactly same to the representation of the plain text. So here, like by translating these letters back to these numbers back to the letters, we get exactly our plain text. So this is the code, and we perform this code on this message. Let's perform this implementation or code on another message using different bound for the characters or for the representations. In fact, here we use the bound for M as 4999, and we perform this like code on this message, which is implementation of ITRU crypto system. And here are the output, and in fact, as you see here, the representation here, this is Q, and this is the public key, this is the private key, this is the corrupted message, and here we get like the decryption procedure, and here finally we get the representation of the decrypted message, as you see here, starting with 73109, and by translating this back to letters, we get our message, which is the implementation of the crypto system. Now let's perform, or let's go to the second step, which is the attack, or performing the attack. In fact, I will perform the attack on another text or another example. Suppose that we have this paragraph, and this paragraph we got it from the ITRU crypto system paper. And this paragraph, suppose that it is corrupted using the ITRU crypto system with these public keys. Okay, using this Q and this H, and actually this Q and H performed using like the upper bound for the representations is 4999. So the idea here, this message, the previous message, is corrupted using these public keys, and here we have like by plugging the previous message instead of like, for example, cryptanalysis in the previous code, which I just mentioned, we get the following ciphertext starting with this 7028293 and so on. So here, the idea here, suppose that we have only this ciphertext and we have only this public key, and we don't know anything about the private keys. How can we perform this attack? So the first step here, a little analysis on the representations of the ciphertext. We have, in fact, 32 numbers appearing between these two numbers, okay? Appearing between these two numbers. So performing a simple frequency analysis here, and this will be presented by Sage Math using this function, frequency distribution, to get the frequencies of the representations of the ciphertext. And here are the representations. As you see, for these numbers appearing, the 32 numbers appearing in the ciphertext. Okay, so we have these, as you see here, here are the representations for each number. Okay, and as you see here, if you take a look, you will find the largest frequency presented by this number, which is 01, 096, and so on. And this actually going for this ciphertext represented number or presented, which by 7028310. So this means this number with highest frequency is appearing the most in the ciphertext. So since this number is appearing the most in the ciphertext, and as you all know, in the English language, the most common letters appearing in English are E, A, T, respectively. So if we suppose this number, which has the highest frequency, is E, and E, according to the ASCII code, it is represented by 101. Then by performing this formula, which is CI minus this number 7028209, and this actually, we got this number by subtracting this number, which has the highest frequency, minus 101. Then, in fact, by plugging the ciphertext representations here in this formula, we get, in fact, this representations starting with 84, 104, 101, 103, and so on. By translating these numbers here in the yellow color back to letters using this ASCII code, we get exactly our plain text message. In fact, you can apply this idea on any message encrypted using the ITRU crypto system, with knowing only the encrypted message and knowing the public key. And by using this code or the frequency analysis technique presented in the Sage Math, and actually here by following the same idea, you exactly get the plain text. Actually here I should mention, like earlier here, as you remember here, I said like this, a little like analysis on the representations of the ciphertext. These 32 numbers appearing between these two numbers. In fact, you may have like different ranks for the ciphertext representations, but the idea will be the same. The frequency analysis can be applied on these ranks, and it can do the work exactly the same. So this all what I wanted to talk about, and I hope it is interesting for some of you, and thank you so much for having me in this conference, and I hope you enjoyed it, and I hope you will have a great time at the conference. Thank you so much, and I wish you a great day. Thank you.